The adoption of the gas turbine engine as the power unit of choice for military and subsequently civil aircraft became more and more the norm after the end of World War II. During World War II, the war effort required every drop of gasoline, and partly because it was thought that gas turbine engines were relatively insensitive to the properties of the fuel they used, but mainly because it was more available than gasoline, kerosene was chosen to power them. After the war, the United States Air Force started using a fuel in gas turbine engines which spanned the gasoline and kerosene boiling ranges. This fuel was called a wide-cut fuel, a name which stemmed from the position in the catalyzing process from where the fuel could be taken. It was assumed that during wartime conditions, wide-cut fuel would be available in greater volume than either gasoline or kerosene alone. However, when it's compared to a kerosene-type fuel, the higher volatility of the wide-cut fuel gives it some operational disadvantages. At high altitudes, wide-cut fuel evaporates much more quickly. There is a greater risk of fire and explosion when wide-cut fuel is being handled on the ground. A crash of an aircraft fueled with the wide-cut fuel is less survivable than if the aircraft had been fueled with a kerosene-type fuel. Because of these disadvantages, the United States Air Force commenced changing from the use of wide-cut or JP4 fuel back to kerosene-type or JP8 fuels in the 1970s. JP stands for jet propulsion. As far as the commercial jet aircraft industry was concerned, kerosene-type fuel was chosen because it appeared to have the best combination of properties. Having said that, Jet B, which is a wide-cut fuel, is still available in some parts of Alaska and Canada because it's suited to cold climates. In the remainder of North America, Jet A, which is a kerosene-type fuel, is used because of its lower cost and better availability. With the exception of the Commonwealth of Independent States, the rest of the world uses predominantly Jet A1, which is also a kerosene-type fuel. Jet A1 has a higher freezing point than Jet A, which makes it more suitable for use on long international flights. The Commonwealth of Independent States and parts of Eastern Europe use a Russian fuel, TS1, which is a light kerosene-type fuel. Jet fuel is produced in a petroleum refinery by processes that can be divided into three basic categories. They are separation processes, upgrading processes, and conversion processes. In a petroleum refinery, the most widely used separation process is that of distillation. Petroleum products can be defined by their boiling range, and distillation is the process used to separate a mixture with a wide boiling range into products with narrower boiling ranges. The separation is achieved by heating the crude oil in a distillation column until the lightest components are vaporized. The vapors are then collected in a condenser where they turn back into a liquid, which is then collected. The lightest hydrocarbons, propane and butane, rise to the top of the column and are removed first. Gasoline, which is heavier, doesn't rise so high in the column and is drawn off from the side of the column. Kerosene and diesel, which are the next heavier fuels, are drawn off at successively lower points on the column. Finally, the residual, which can be further refined by a catalytic cracking process into lubricating oil, paraffin wax and asphalt, is drawn off at the bottom of the column. The quality of the light products generated by distillation alone is often poor, so the refinery must use conversion processes, like the catalytic cracking just mentioned, and upgrading to bring the fuel to a standard which is suitable for its task. Upgrading processes are used to improve the standard of the fuel by using chemical reactions to remove any compounds which may give it undesirable qualities. One such upgrading process is called sweetening. Sweetening converts sulfur mercaptans in the fuel into disulfides. While sulfur mercaptans are corrosive and have a strong offensive odor, the disulfides are not corrosive, and their smell is less strong. The two leading organizations which set and maintain specifications for civil aviation turbine fuels are, in the United Kingdom, the Ministry of Defence, or the MOD, and in the United States, the American Society for Testing and Materials, ASTM. In the Commonwealth of Independent States and parts of Eastern Europe, gas turbine engine fuels are covered by GOST specification. The specification of an ideal fuel for a gas turbine engine would include the following requirements. The fuel must be able to flow freely from the aircraft's fuel tanks to the engines. Fluidity is a general term that deals with the ability of a substance to flow, but it is not a defined physical property. However, viscosity and freezing points are physical properties, and they can be used to characterize the fluidity of gas turbine fuels. Viscosity is a measure of a liquid's resistance to flow. A thin liquid, like gasoline, has a low viscosity, and a thick liquid, like treacle, has a high viscosity. The viscosity of a liquid increases as its temperature falls. Gas turbine fuel is composed of more than 1,000 individual hydrocarbons, each with its own freezing point, so it does not become a solid at one temperature in the same way that water does. As the temperature of the fuel becomes lower, the hydrocarbons with the highest freezing point freeze first, and form wax crystals. As the temperature drops further, the hydrocarbons with slightly lower freezing points start to solidify, and so on as the temperature falls even lower. Thus the fuel changes gradually from a homogeneous liquid into a liquid which contains a few wax crystals, then to a slushy liquid composed of fuel and wax crystals, and finally to an almost solid block of wax crystals. Small carbonaceous particles are formed early in the combustion process within a gas turbine engine. In ideal conditions within the engine, the particles would be completely consumed, but conditions seldom remain ideal, and if they impinge upon the nozzle guide vanes and rotor blades of the turbine, the particles will erode them. Fuels differ in density and therefore in energy content per unit weight or unit volume. Less dense fuels have a higher energy content per unit weight, as for instance aviation gasoline, which has 18,800 British thermal units per pound. But they have a lower energy content per unit volume. In this case, 112,500 British thermal units per gallon. The relationships are reversed for denser fuels like kerosene, which has only 18,610 British thermal units per pound, but 125,800 British thermal units per gallon. Corrosive compounds are inevitably present in the fuel used to drive gas turbine engines. The corrosive agents include organic acids and sulfur mercaptans, which are potentially very damaging to aircraft fuel systems. Additionally, the fuel becomes contaminated by trace amounts of sodium and potassium, which can corrode the turbine. Ideally, all these should be eliminated from the fuel. The flash point of a liquid is the lowest temperature at which the vapours above a liquid will ignite when they are exposed to an ignition source. The higher the flash point of a fuel, the lower the fire hazard it presents. We have just seen that to burn, the fuel must turn from a liquid state into a vapour. Volatility is a fuel's ability to vaporize, so it's important that the fuel is reasonably volatile. However, if the fuel is too volatile, it will evaporate quickly when the aircraft is at altitude, and it could cause vapour locks to occur at the inlet to the fuel pumps. Lubricity is the ability to reduce friction between solid surfaces which are in relative motion. Gas turbine engine fuels must have a degree of lubricity, because the fuel is used as a lubricant in the pumps. These requirements can be met, and the various methods used to achieve them are discussed later. However, in practice, the cost of satisfying all of them is prohibitive, and therefore compromises have to be made. We've already stated that the gas turbine engines of commercial aircraft would normally use kerosene fuels. The types of fuel which can be used in gas turbine engines are listed here, together with some of their characteristic properties. Jet A1, or AVTUR, which is short for aviation turbine fuel, is a kerosene-type fuel with a nominal specific gravity of 0.8 at 15 degrees Celsius. It has a medium flash point of 38.7 degrees Celsius and a waxing point of minus 50 degrees Celsius. Jet A is also a kerosene-type fuel with a medium flash point, but it has a waxing point of minus 40 degrees Celsius. This fuel is normally only available in the United States. Jet B, or AVTAG, which is short for aviation turbine gasoline, is a wide-cut gasoline kerosene mixed-type fuel with a nominal specific gravity of 0.77 at 15 degrees Celsius. It has a low flash point of minus 20 degrees Celsius, a wider boiling range than Jet A1, and a waxing point of minus 60 degrees Celsius. This fuel can be used as an alternative to Jet A1, but, as we stated earlier, with its low flash point, it's a very flammable fuel, and for reasons of safety is not generally used in commercial aircraft. Turbine fuels are not dyed. They retain their natural colour, which can range between what is referred to as water clear to a straw yellow. If a fuel sample is placed in a clean, transparent, dry glass container and swirled vigorously to generate a vortex in the sample, and the sample appears cloudy or hazy, this could be caused by a number of factors. If the cloudiness appears to rise quite rapidly towards the top of the sample, then air is present. If the cloud falls quite slowly towards the bottom of the sample, then water is present in the fuel. Having said that, a cloudy appearance usually indicates the presence of water. A certain amount of water is present in all fuel. The water, which is normally dissolved within the fuel, gives rise to the following fuel system problems. As an aircraft climbs to altitude, the fuel is cooled, and the amount of dissolved water that it can hold is reduced. Water droplets form, and as the temperature is further reduced, the droplets turn to ice crystals, which can block fuel system components. Microbiological fungi called Cladosporium resinae and Pseudomonas aeruginosa are present in all turbine fuels. These fungi grow rapidly in the presence of water to form long green filaments, which join together to form dark, gel-like mats. The filaments and mats can block fuel system components. The waste products of the fungus are corrosive, especially to fuel tank sealing substances. The inclusion of a fuel system icing inhibitor, or FSII, in the fuel will help to overcome these problems. The inhibitor presently in use in all countries except Russia is diethylene glycol monomethyl ether. Not only does it inhibit the ability of the water in the fuel to freeze, it also acts as a pesticide, which retards the growth of the microorganisms in the fuel. Lubricity agents are added to the fuel to compensate for the poor lubricity of some gas turbine fuels to reduce wear in the fuel system components. Gas turbine fuel in its untreated state is a poor conductor of electricity. Static dissipator additives partially eliminate the hazards of static electricity generated by the movement of fuel through modern high-flow rate fuel transfer systems. Corrosion inhibitors protect ferrous metals in fuel handling systems, such as pipelines and storage tanks, from corrosion. Certain of these corrosion inhibitors appear to improve the lubricating qualities, the lubricity, of some gas turbine fuels. Metal deactivators suppress the catalytic effect which some metals, particularly copper and zinc, have on fuel oxidation. Copper and zinc are not used in most jet fuel distribution systems or gas turbine engine fuel systems, but if the fuel does become contaminated with either of these metals, metal deactivators inhibit their catalytic activity. We've already stated that water is always present in fuel. The amount will vary according to the efficiency of the manufacturer's quality control and the preventative measures taken during storage and transfer. Further measures can be taken to minimize water accretion once the fuel has been transferred to the aircraft tanks. If the fuel can be allowed to settle after replenishment, then the water droplets, being heavier than the fuel, will fall to the bottom of the tank and can then be drained off through the water drain valve, which is situated in the lowest part of the fuel tank. Heating the fuel before it's passed into the more sensitive components of the system will assist in preventing ice formation. In gas turbine engine fuel systems, the fuel is passed through a heat exchanger which is powered by compressor delivery air to melt any ice crystals which may have formed while the fuel was exposed to the very low temperatures experienced at high altitudes. Some systems also utilize a fuel-cooled oil cooler. This has an added attraction in that we appear, just for once, to get something for nothing. After all, the oil has to be cooled, and the fuel benefits by being warmed, so 2 jobs for the price of 1. Once the fuel is in the aircraft fuel tanks, the main source of water contamination is the atmosphere that remains within the tank. If the tanks are topped up to full, then the atmosphere is excluded, together with the moisture it contains, thus minimizing the likelihood that the fuel will be contaminated. Caution is required here. Filling up the tanks may prove an embarrassment the next day if the ambient temperature rises. The volume of the fuel in the tank will increase, and there is the danger that it may spill out of the vent system. We've already spoken of the process whereby, as the temperature of kerosene becomes lower, the hydrocarbons in the fuel which have the highest freezing point freeze first, and form wax crystals. The wax crystals can clog the fuel filter and interfere with the operation of the fuel control unit. The effects of waxing can be minimized by the refinery keeping the levels of heavy hydrocarbons in the fuel to a low level, and the inclusion of a fuel heater in the engine fuel system. The specific gravity of a liquid varies inversely with its temperature. The heat release from the fuel is directly related to its specific gravity, and so changes in fuel density can change the power output of an engine. On modern aircraft this usually makes little difference, as modern fuel control units will automatically compensate for the change in density of the fuel. Remember, though, that a change in specific gravity will also change the weight of the aircraft. Specific gravity is also known as relative density. This concludes the lesson on gas turbine engine fuels.